So what I'd like to do is to rehearse our curve sketching tools so far. And we have a number of them. And they're all expressed in terms of theorems. And our theorems, you all ready? Okay. Our theorems basically allow us to characterize, first of all, local maxes and mins. Second of all, increasing and decreasing. And third of all, concavity and inflection points. Really something's going on. You care to share? I'm just hearing a lot of chatter. Alright. So, Fermat's theorem says what? Yes. Yep.
We're talking about money.
Okay.
Focusing. Fermat's theorem. Tell me Fermat's theorem.
Well, let me see.
Uh-oh. He's lost. Fermat's theorem.
If F is a maximum, then F or FC, then MC is a MC.
Perfect. What's our slogan for that? Good. And Justin, what kinds of critical points do we have?
Yeah, and I'll change this row of the sign off.
Okay, so actually that's a little different question here. I'm asking what types of critical points do we have?
I'll continue with the history.
Uh-oh. What are they?
One is F prime equals 0 or
Yeah. Notice that I am blatantly quizzing you about language because it's necessary that you know the vocabulary and the theorems. So if you have not yet embraced the fact that you need to know those vocabulary and theorems, do not resist any longer. Join the fluent side. Okay? Now, in addition to Fermat's theorem, local extrema only occur at critical points, we have a theorem that allows us to characterize those critical points, and that is our first key test. Elliot, give me the first key test.
I try and change sign. If change from negative to positive, which means it's local mean.
Okay? Let's put our language in full terms here. We need a location that you're talking about. If F prime changes signs where?
X.
X equals 0.
And now what are our possible sign changes?
Case 1 is from negative to positive.
Then,
FC is local mean.
good. And what are our other possibilities?
From positive to negative. Then FC is local x.
And what happens if F prime does not change signs?
Which means FC neither mean or max.
Very good. So the first t-test is in some sense a complete test in that I can observe sign change, and here it is. Now, the one kind of function that will work with the first t-test is actually your constant function, where there are no signs of f prime at all, and so the first t-test does not apply. Notice that a constant function has the weird property that every single point is a local max and a local min, and that f prime of c is equal to 0 constant. Okay, so these are the local max and min finders. In addition, we can characterize the function in terms of increasing and decreasing. And we have a partial but powerful result. And the AP, or simplified version of this, is that if f prime of c is positive on an open interval a to b, then f is increasing on that same interval a to b. Notice that we require open interval for this theorem to be valid here. However, at endpoints, we can still talk about increasing through, right? The converse of this theorem is false. It is not true that every increasing function on an open interval has a positive derivative. We gave as a counterexample f of x equals x cubed, which is increasing on the entire real line, but has a 0 derivative at x equals 0. Likewise, if f prime of c is less than 0 on a to b, then f is increasing, decreasing on a to b. So much for increasing and decreasing. Then yesterday we considered concavity, and we had a threefold kind of relationship here. If f double prime is positive on the open interval a to b, then the following things are true. F prime is increasing, which is a direct result of this theorem right here applied to f prime. F is concave up on a to b, and f lies above its tangents. The picture that you want to draw here is of a function that is either decreasing or increasing, but its derivative is increasing. Therefore, it lies above its tangent. If f double prime is less than 0, then the implications are exactly the opposite of above. F prime, b, f prime is decreasing, b, f is concave down, f lies below its tangents. And then we considered where concavity changes. And concavity changes at inflection points, or points of inflection. And a universally recognized abbreviation is POI, which is not a type of goldfish.
What? Goldfish? Why is goldfish?
Koi. Yeah, the big goldfish, koi fish.
Yeah, yeah.
Okay. Yeah. Now, what can we say about points of inflection? Three things.
The concavity change,
Concavity changes. So how do I say that in terms of F double prime? Changes signs. Good. And we avoid the newbie mistake of saying F double prime equals 0, right? We don't do that. Because we recognize that sometimes F double prime could be 0 and fail to change signs, in which case our curve is nice and concave up even through the 0 of F double prime. Or concave down, whichever it is. F double prime changes signs. What about in terms of F prime? Yeah, local extreme limit. For F,
Because of tangent equals to
yes, crosses its tangent.
so like all of this is like, it's a visual, equivalent.
Yeah, and I'm backing away from calling it an equivalence because there are some weird exceptions that happen here. Everything that I've said here is true. However, if you try to do converses, things get strange. So for example, F is concave down does not imply that F double prime is less than 0. It could also have isolated zeros. But it does imply that F prime is decreasing, because this is a matter of definition. That's what it means to be concave down. And I believe it also means that F lies below its tangents at each point. Searching through the literature has not given me closure on the way to capture exactly the circumstances under which we get it moving. And I'm still kind of working on that. But definitely it is the case that if F has isolated zeros, excuse me, if F double prime has isolated zeros and the sign does not change, then concave down on the entire limit. But I'm not sure what happens in the weird case where F double prime has non-isolated zeros, where the zeros of F double prime are dense in the real world. I'm still trying to hunt that down. Certainly, any normal function that you will encounter on the AP exam is not going to have anything weird like that. If F double prime is 0 on an entire interval, then that simply means that F prime is constant on an interval, and our function looks like a straight line. So I'm gonna retire the threefold equivalence term temporarily until I can get some closure on that issue. We can call it a threefold implication. Yeah. If the sign of F double prime is nice and constant, then that implies these three things, and point of inflection implies these three things. Okay? Okay. What I'd like to look at today is the second d-test. And the second d-test is a local max and min finder also, just like the first d-test is. The second d-test is a little more specialized because it doesn't always work. Sometimes it fails to give an answer. It never gives false answers, but sometimes it fails to give an answer. But the payoff is that it is sometimes easier to use than the first d-test, and sometimes it is the only thing that can be used. And I shall demonstrate both of those things. here's the second d-test. Suppose f double prime, excuse me, f prime of c is equal to 2. So we have a critical point, Justin, there's our vocab, critical point of the first type, where we have a horizontal tangent. And let's draw two cases. Let's draw the case where f double prime of c is less than 0. In that case, I'm looking at a curve that is concave down. And when I draw my horizontal tangent, I see that the only way for this to be the case is for f of c to be a local max. If, on the other hand, f double prime of c, let's do this, is greater than 0, then this must imply that f of c is a local min. If none of these cases obtains, so what are the other possibilities here for f double prime of c? Equals 0, exactly, or does not exist, that's right, fails to exist, then the test fails. Otherwise, our test fails. Now, let's get a proof of this. The proof is kind of nifty. And I want to observe that I cheated a little bit because I drew my curve as concave down on this entire interval. But actually, I don't really know that my curve is concave down on an entire interval because I never said anything about f double prime of c being negative on an interval. I only said that f double prime of c is less than 0. So that actually takes us a little bit out of the realm of this stuff right here and into the case where f double prime of c is negative at a single point. What implications can I draw? Well, actually, we already have the tools to deal with this. Suppose f prime of c is 0 and that f double prime of c is less than 0. This means that f prime is decreasing through c. Think about this for just a minute. What this is saying, because the derivative of f prime is negative at c, therefore f prime is decreasing through c, which means that there is a neighborhood of c such that when x is less than c, then f prime of x is greater than f prime of c. This is what it means to be decreasing through. If I go to the left, I go up. And if x is greater than c, then f prime of x is less than f prime of c. In other words, if I go to the right, I go down. But what is the value of f prime of c according to our hypothesis? 0. So what have I just said? I have just said that f prime of x changes sign from positive to negative. Hey, that's the first t-test. That's an x. Ta-da! Yeah, we like that. Well, the second part of the argument is going to look really similar. Suppose f prime of c equals 0. And f double prime of c is greater than 0. And then what can I say? Somebody construct my argument for me.
So that F is
Not f,
Prime.
but
prime.
prime, yes. Because it's f double prime is the derivative of f prime. F prime is increasing through c.
That is the neighborhood. And when it's smaller, it's F prime is smaller.
Which is 0.
That's bigger than C and prime is bigger than so it's a local min
Yeah, let's go ahead and say the obvious. That means f prime is changing signs.
from negative to prime.
C, so f of c is a local. Good, very good. Okay, now I want to observe a question about style. You notice that I had you insert this thing right here. And the question is it really necessary? And that's actually a matter of style. If you look in older math textbooks, they have a tendency to lead up connecting sentences like this. And as a result, the older math textbooks are short, you're saying. So like Rubin, which I'm still looking at here, and it contains more material than this book, or even either of these books. Because basically he writes math, does math in a very condensed style, which expects the reader to fill in details. As time has gone on and paper has gotten cheaper, I think I'm kidding. It has become more fashionable to include these connecting sentences to allow the reader a better chance to understand what's happening. Right? And so what we did here, this connecting sentence was the conclusion of this statement right here, and it was also the hypothesis needed for the first details. And so we consider this a stepping stone statement. It kind of helps clarify things. Let's just start. Okay? Good. Good, good, good. Now, second d-test. Let's take a look at places where we might use the second d-test. Find the local extrema of, should look fairly familiar. To find the local extrema using second d-test, we need to establish two things. First, that f prime is 0, and second, that f double prime has a certain sign. So we consider, first of all, f prime and its critical points. And our critical points are root 2 and negative root 2. Now we consider f double prime of x. And we evaluate f double prime of x directly at each of the critical points. And we provide value with obvious point greater than 0 here, And we appeal to the second D test to say that f of root 2 is a local min. And there you go. What are the advantages and disadvantages of using the second D test here compared to the first D test?
In this case, it's not any faster though.
It's not necessarily any faster, yeah. It's about the same, really, in terms of total work done. What I do not have are any number lines, right? There's no well-labeled f prime number line, I don't need it, because I don't need to see sign changes. The f double prime analysis takes care of those sign changes for me, basically.
So what's the disadvantage?
A disadvantage is that it might possibly fail. So let's look at an example of failure here.
Then it goes into our generic list. Instead of we can use the first defense.
Yeah, that's right. So just a simple example, f of x equals x to the fourth. Find the local extreme. So I do the same process here for x cubed, set it equal to 0, get a single triple root at x equals 0. The triple root is the sign of a problem. That's really where things are going to fall apart for us. And now when I consider f double prime is 12x squared, and I evaluate at 0, I get 0, no information, or test fails, or some other way of saying does not apply, didn't tell us an answer. And so I must go back to the first D test
Oh, another thing that.
and
And then,
consider the first D test here when x is less than 0 negative, when x is greater than 0 positive. What's happening here with this curve geometrically is that f of x equals x to the fourth is very tall and skinny, and right here at the bottom, it's very flat. And the reason that it's so flat is because of that triple root. The triple root forces f double prime to be 0. In fact, f triple prime is also 0. And it's not until you get to the fourth derivative that you finally get a positive value. It's possible to extend the second D test. I'm just going to throw this out there with some more. To say that if all of your derivatives are 0 down to 2n plus 1, or 2n minus 1, and the 2n plus 1th derivative is positive, then you have a local min. 2n plus 1 derivative is negative, then you have a local max. I think the proof of that goes by induction. So here we have a local extreme. Now, Elliot, what's the language we have to wrap around this? We have to say that f of 0 is a local min. And here we need to actually interpret the number line by saying because f prime changes sign minus plus. This is the magic language that I require for all of that. And there is a specific reason I require it, because AP requires it also.
Did you take points off?
I did. That's the only point you missed. We're failing to give me an argument. Yep. Now, I want to consider a different situation here. I want to consider an example where the second D test is our only hope. Let's take a look at this problem. Find the relation x squared plus 4xy plus 4y squared minus 3x is equal to 6. And this equation right here is an interesting relation, and it defines what we call a generalized conic section. This one happens to be a parabola, and you can tell by computing what's called the discriminant. So if we have this is a generalized conic section, and it includes circles, ellipses, hyperbolas, and parabolas. And it is possible to show, although I will not go there at this time, that all of these can be found by simply taking a double cone like so and passing a plane through the double cone. And if the plane that you pass through happens to be exactly parallel, that's horrible. Let's have our plane pass through like this. If our plane passes through like this, so that it intersects the cone like so, then what you're going to get is a hyperbola for your conic section. Make our plane wider. So it cuts through like this, and what you're going to get is a hyperbola because you're cutting through the cone. This is hard to draw so that it makes sense. You know what? I'm going to kill this plane because that plane isn't showing what it needs to show. So if you pass a plane through here, like so that it cuts here and here, then what you're going to end up with is a hyperbola. But if you pass it through so that the plane is parallel to the cone, like so, then you're going to get a parabola. And if you pass the plane through so that it cuts like so, then what you're going to get is some kind of an ellipse. And if the plane is perpendicular to the axis, you get a circle. So all these are called conic sections because of the double cone that produces them. And it's possible to show that these conic sections all have this kind of equation. And in particular, we can characterize which one of these with the discriminant of this equation right here. If b squared minus 4ac happens to be greater than 0, then we're looking at a hyperbola. If b squared minus 4ac happens to be less than 0, we're looking at an ellipse. And if b squared minus 4ac happens to be exactly equal to 0, then we're looking at a parabola. And in fact, that's exactly the case as you see here. If I do b squared minus 4ac, then I get 0. So we're looking at some kind of a parabola, and that parabola would be generated by rotating the axes by a fixed amount, and it's going to end up looking something like this. Now I want to ask a question. I think we already know the answer to the question, but maybe I drew this wrong. So, where are the horizontal tangents, and do they correspond to local maxes or mins? So find the local extrema now of this curve based on this relation. Okay? So that's our job. So to find the local extrema, first I have to find the horizontal tangents. And this is a job for implicit differentiation method. And work with me here. Derivative of 4xy should be
4xy equals 4.
good. Derivative of 4y squared.
4
A, Y, Y.
Minus 3. Good. so that I get now collecting terms with y prime, collecting terms without y prime. Now, I picked this problem out of a hat, so it may get yucky, but we're great. If I want y prime to be equal to 0, then what does that imply?
2x plus 4x minus 2
Exactly. So that what this tells me is that my horizontal tangent is going to be found along the line y equals negative 1/2 x minus 3/4. In other words, it's going to be found along this line right here. So my curve is probably a little too high up. Might be something like this. Or my horizontal tangent. Where my horizontal tangent takes place is going to be found at the intersection point of this line and this curve. And you can see right here the line in red, the horizontal tangent that we're talking about. Okay, so how do I find that point? I know the line that it's on, I know the curve that it's on, it needs to be at the intersection point. Aha! That means that the two curves intersect, and therefore I can substitute into the original relation and get an equation that can be solved. I think this is a job for graphing calculators. So, let's take and substitute into our original relationship. So that we have x squared plus 4x times negative 1/2 x plus minus 3/4 plus 4 times negative 1/2 x minus 3/4 squared minus 3x is equal to 6. Definitely we want to do this on the graphing calculator. Go ahead and solve this equation and find the x value. I'll pause while you do. Okay. Yeah, so one of the things that I observed about this as I was looking at it is that I have a term with x squared here, and I am going to have a term that is going to be 1x squared here, a fourth of x squared times 4. And over here, I'm going to end up with negative 2x squared. So all my x squareds cancel out, and in the end I get a linear equation. And the single solution that we get is x equals negative 1.25. This is our critical point, found by setting y prime equal to 0. Now, here's the point I wanted to make about this problem. Max or min, I can't use the first d-test. And the reason I can't use the first d-test is that my y prime here depends both upon x and on y, and as x changes, I don't know how y is going to change along with it. So using the first d-test here is, at the very least, highly improbable, if not impossible.
You can't really draw them.
You can't really draw the number line very well.
Yeah.
So, instead, we're going to appeal to the second d-test. Unfortunately, that means taking the second derivative here. Fortunately, when we get to the crucial moment of evaluating y double prime, we will not have to do a whole lot of horrible algebra. So let's find y double prime based on y prime. Going to our second page. Let me just copy y prime over from the previous page, actually. There. Okay. So y double prime then will be the derivative of this guy. A bit of a pain in the neck. The derivative of this would be 2 plus 4y prime minus I below plus 8y first, we look at this and go, oh, this is gonna be horrible. But then we realize that in fact, this is not so bad off because we have values. We have a value for x, we have a value for y prime, it's 0. And we know that the entire denominator is positive, so we can effectively ignore it. The only thing that we're lacking is a value for y. So we need to go back and find that value for y. Here's our original relation. And we know that x is equal to negative 1.25. This is fairly detailed analysis, is it not? And all that is equal to 6. Go ahead and find y. Actually, I think we can be smart about this because we had two relations between x and y. One of those relations was y equals negative half x minus 3/4. So why not use that relation instead of the hard relation? I like that. So if y is equal to negative half x minus 3/4, and x is negative 1.25, this gives us, oh, I don't know, positive 3/4. Really? I don't know. This is 4. So positive 5/8 minus 3/4, which is negative 1. And we've got a value for y. Ta-da. Okay, now it's a matter of plugging in. Y prime is 0. All of that over something positive. Now when we examine each of these terms, this term is negative, this term is negative, this term here is going to actually end up being positive because of the double negative.
Replace minus.
Overall, the whole thing is minus.
No, I mean, it's minus positive, this will be negative.
Yeah, let's actually work it out. This is negative 5, minus 1 is negative 6, times 2 is negative 12. In the first term, minus, this is going to be minus 5 halves, minus another half is minus 6 halves, or minus 3, minus another 3 is minus 6, times 4. And so I get positive 12 over something positive, which is going to be greater than 0. So that I can conclude that we have a loop. This was a detailed analysis, and it is not the kind of thing that you necessarily have to do a lot of, but you can see why.